We also have hotspots across ridge axis, which support the idea that plumes come from very deep. They start up from the bottom boundary layer, and then they're oblivious of what they're going to run into when they do this. We have the Mata region of all New England magnetic province. Seamounts here. We have a gap here that's interesting that's due to dynamics. The hotspot is here, and then it jumps and leaves a region with very little volcanism, forming an on-ridge hotspot. The hotspot ends up on this side of the ridge and goes to Great Meteor Seamount. This gap is not really interesting. It's just from C4 spreading from this and this were adjacent. So this gap is just simply from kinematics. It's dynamic math. We don't know whether it's shallow flow of material into the ridge axis like I was showing in the discovery, or whether the mantle wind bends the plume into the ridge, and it's a deep dynamic process. This is something that's not resolved, and I'm going to be keeping there. Ridge leaving hotspot, Hawaii. Hawaii was on the ridge axis, and now you think of it as in the middle of the plate. So the on-ridge and off-ridge hotspots seem to be the same pattern. So to point out the analytical solution here, the plume material is spreading slowly, not convecting, not changing very much. This is a long-lived situation, so it's what we might see if we look at something randomly. Again, we don't know whether the plume material has channels of hot material, it's low viscosity, or whether these surface lines of small volcanic edifices that we see are just due to dikes. We have a thin layer of plume material, thickness at the top of the plume material here that convect ends up scaling to the total thickness of low viscosity material here that can act as a conduit. And if the plume material is going to be thick, it's going to flow fast, and the long-lasting state is it's going to be thin, and the physics of the rheological boundary layer and the flow through a conduit turn out to have the same scaling. This traditional formula, Jouet formula for conduit flow, we have a dependence here on the thickness of my conduit of plume material. Q, this is a quantity. Plume material currently cools, but it's going to be conserved to some extent, and it's the quantity that controls the spreading of plume material. If this quantity is large, the material is going to spread. Plume material is going to get thinner, and then the spreading is going to cease. We can also write the stagnant lit convection formula, and the bigger of convection, this is the Nusselt number, which is the ratio between conductive and convective heat flow. We have a dependence here on the temperature to change viscosity over E. Again, we have Z cubed over our relevant viscosity, so the two terms are going to be very closely related. Conditions that will result in vigorous spreading are going to result in vigorous convection, and both the convection cooling the plume material and the spreading it of the plume material are going to, in one case, spread the plume material, in the other case, do away with its thermal buoyancy, and we're going to end up as a long-lasting state with plume material flowing sluggishly. And again, we have the two-dimensional equations with CQ, and the rate of spreading is proportional to this Nusselt number. This is the slope of the lithosphere, and we have the temperature, total temperature difference, and the temperature difference driving convection, which is a factor of Q. You have the critical Rayleigh number, which is basically something determined by physics. And so the vigor of convection, which is parameterized in this number, the vigor of spreading are both proportional to each other. And the long-lived state, both of these will be relatively small and not zero. Okay, again, back to the data here. And we would like to address the viscous fingers here. It's easy to do 3D models of a sluggish flow. They just dump in a batch of material and let it go quickly. The part here that's spreading up a lithospheric slope will self-organize, and it will self-organize to slow flow that does not channel. And in the map view here, you do not have a channel, and the material just peacefully spreads laterally before it becomes thin, where it neither convects nor spreads laterally. In cross-section here, we have the material spreading. It's channelized by the side boundaries here in the model, but it simply spreads out the lithospheric slope, and we do not have strong contour variations here that would indicate vigorous convection. However, if you dump very hot plume material beneath pre-existing lithosphere in the model, this is a 2D model. Note this great vertical exaggeration. You end up notching the lithosphere very rapidly, and these notches preferentially can become channels. And hot material will erode the lithosphere. This is a model where we do put in hot, very low viscosity material, and it has ended up producing areas both high temperature and thin lithosphere. We have two notches here just from the particular symmetry of the models. The answer here is I don't really know what the case. We can get models to behave in both directions. So again, emphasizing what we know and don't know. Get closer to here, we go a little bit to the west, we have a nice passive margin. We have a thick evolving shield, osmograben, and then we have the passive margin out here. The plume was underneath Greenland rather than underneath Scandinavia at the time, but we had the plume over near Stockholm. We would have got plume material coming up, flowing, ponding in the area where there was somewhat thin lithosphere around Oslo, coming across here where there's somewhat thicker lithosphere, and then spreading over the passive margin. Okay, we can have the plume material as off the coast of South America, off of Brazil, get trapped underneath, and then the plume material under bottom can get released over a short period of time. We'll show some photos from Martin and Fernando. We'll see this on Africa. And we also have continental margin crossing plumes, which I've shown you some of already, where you get the spillages. We have tracks like this that are old, the typical Atlantic track direction. We have tracks here that follow flow lines. There's a plume somewhere probably down in here that was probably north up here, probably across the Amazon 40 or 50 million years ago. There's poor age progression in these tracks, and we have lines that are just flowing downhill in the lithosphere towards the ridge axis. That's something that can be relatively easily displayed. We put a big plume in here, possibly a second plume here. There's a network of rift valleys, many of them Cretaceous, underneath the ridge axis. The plume material gets in the corridors of thin lithosphere, spreads out here down to the coast of Madagascar. Extensive intrusions here off the coast of Somalia. They, again, you see the map here, spread around here and form the any seismic ridge here that's currently active. It's confusing because it's coming in where the ridge axis is. There may be a plume here and a plume here. This is possibly a two-tailed starting plume head. One plume head is coming up. The second plume head overtakes it. The two heads merge. They come up together and produce a two-tailed plume. This is one of the possible examples of it on the Earth. And don't ask me within 500 kilometers here where I think the Victoria plume is.